Well, hi, hello. So today we're going to be going over an introduction of limits and how to find limits numerically. When it is said to find something numerically, that means we're using a table in order to evaluate, for this case, a limit. So typically I don't have the do now in the first part of my video, as you may call it, but it's important to go over the basics. I mean, it is called an introduction to limits. So here it says in pre-calculus, we learned that a limit is an intended height of a function. Okay, so the intended height is usually like the y value, okay? And the limit is the value we're trying to see, like what it can be, like what its boundary is, like what is that y that it's trying to get to. So, for example, why we say height is because let's say we have a function. It is defined, I guess this is a nice semicircle. Oh, who am I kidding? That's not a semicircle, but, just bear with my drawings. So if, let's say, we wanted to find out the intended height for, let's say, this x value, x equals c, then we would notice that it makes sense. It seems to be going up to about this point here, and it seems on this side, same thing. It has to always be the same thing. Okay, it can't be one answer and then another. It's got to make sense. Okay, come together at one place. So the intended height, we would just measure from the top of our function here to the x-axis. Okay, and that's why it would be some sort of y value. Okay. This is the same as saying it's y value. Now, sometimes our graphs are not going to be above the x-axis. Maybe it's down here, and it would have a negative value. So we're not really saying height to say, oh, hey, it's always going to be a positive answer. It's just an idea, like a feeling as to what we're trying to do when we find a limit. And it's some y value that it's going towards. Okay, so it could be a negative value also. Okay, I just want to emphasize that. Kind of fill that in a little bit. So, the idea of a limit of a function is what connects algebra and geometry to calculus. And as you see, I was trying to graph something, so a lot of geometry and semicircles. I even spoke about, measuring this to find a distance. And obviously, algebra, I was trying to draw a function, a very poor-looking function, but as I said, please bear with me with my drawings. So, next. Here we have the limit notation. Be careful how you write it. You do have to write it exactly as you see it here. You should probably be writing it down, and it reads, the limit of f of x, so that's kind of like in the same line. You just kind of read it across. As x approaches, well, in this case, c, okay, we don't know what that x value is, so usually we use c to have some sort of constant there. So the limit of f of x as x approaches c. Then we say what it equals. Okay, then we say, oh, hey, it equals 5, or it equals -5, or it equals 0, whatever we think that it can be, or it actually is. We're going to go over a little bit of a format as to understand when it exists, when it doesn't, and etc. So here we go. Okay, this is something you really need in your notes because it is that outline of what to kind of expect here. First thing it says, a limit of a function, and I'm pointing out that you're trying to find its y value, So the limit of a function a may exist as a numerical value. That's what I was saying in the last part of the video. Maybe it's 5, maybe it's -5, maybe it's 0. Those are all numerical values. Or B, it does not exist. Okay? And when it doesn't exist, maybe we write down an answer that it's positive infinity or negative infinity. But not always. It depends on what's actually going on with the graph. If your y values get arbitrarily large and positive, then you can say it's positive infinity. If they get arbitrarily large and negative, we can say it's negative infinity. Let's say it just is at x approaches c, and that value of c is not in the domain of the function, okay? Then we just write does not exist, or D and E. Okay, as you copy this down, I hope you're listening. And the reason why we do that is because we can't actually give any other answer. It definitely wouldn't have a numerical value, and we can't say, oh, it's positive infinity or negative infinity. It's just nothing. So that's why I wrote for 1B, and maybe but not always. Okay, we can write the answer as positive infinity or negative infinity. Okay, so now that you know a limit of a function can have, various answers. Okay, that was part 1 here. Let's talk about part 2. So you're copying down the limit of a function as x approaches c. Okay, limit of a function as x approaches c. Okay. A may be defined as x equals c. That means f of c has a numeric answer, and that could be the limit. Okay? It could be that, f of c has an answer, but it's not the limit. Okay, the limit has a different answer. And that's what it's saying here in part B. It may not be defined as x equals c. Okay, so be very, very careful. Okay, so you might be wondering, well, if it's the y value, why isn't this the answer? Because it's not the y value of the function. Okay, if you look back at the video, you're going to notice that I'm talking about as you look at your y values going along the function and how it makes sense it's at a particular y value. Okay, it's not always that y value. Okay, it just made sense from both directions. It was going to this particular y value. All right, and I'm sorry for scribbling all over, but we will get to some examples and it'll make more sense. Okay, so these are our examples. Okay, so we have 3 different functions we're going to find the limit for. And the way in which we're going to find the limit of these today is numerically. Okay, you may want to write this down first, even though I put it underneath. So to find a limit numerically is with a table. I said that in the beginning of the video. Tables work most times, determine if there is a limit and what that value of the limit would be, if there is a value. Okay, I say most times because it depends on what your table is, what you set it as for its values. So I'm going to give you two different tables as examples pretty soon, but not yet. All right, so let's look at A, B, and C. So A is a rational function, f of x. B is a piecewise function, where the first piece is a rational function, but it's not defined at x equals 1. For x equals 1, the y value is 1. And C, we have a different function here. H of x is just a linear equation, nice line. So we're going to actually like graph these out, and this gives me the chance to like show you what it would look like if we graph each one. Okay, so since I'm going to be drawing out these graphs on this video, they're not going to look the most fantastic graphs you've ever seen. Just giving you that heads up. If you have a notebook, and you should be doing this along with me, they should look a lot better than I'm going to be able to draw here. So I'm just kind of labeling my x-axis here, hoping to actually fit more than one graph. So let's see if I can do that. Okay, so I previously did this before, and that's why I know my x values can go up by an increment of 1, and the same thing with my y values. I'm going to go up to 5 here, so hopefully I can squeeze that in. There's 1, 2, 3, 4, 5. So on the graphing calculator, if you have a rational function, make sure that you have parentheses for the numerator and denominator. Unless you have a higher version of a calculator, it may set it up so you can just jump up to the numerator, jump down to the denominator. Okay. So now, if you look at your table of values, okay, for this particular function f of x that we're going to draw, let me take a picture of that. Okay, so the table of values I show here, I went up by 1s on my x, and those are my y values. So I'm going to start plotting these points the best that I can. And for when x is 1, y sub 1 says error. Okay, so what's happening is that there's a hole in our graph, because if you actually were to hit the graph, you would see it starts to make a line. And then there's a spot missing. I'm plotting the other points based on my table, more or less. It continues that line. So this is f of x. Nice hole in there. Okay, when x is 1. So now let's go to graphing g of x. Okay, so g of x is a piecewise function. You're going to notice y sub 2 and y sub 3 is how I put in the piecewise function. I'm going to take another picture so you can see y2 a little bit better as to what to put in. Whenever you have a piecewise function, the interval here for the domain has to be divided out. Okay, so if you go to second math, that's your menu for test. It gives you all the different like equal signs, non-equal signs, less than or equal to, greater than to equal, all of those symbols that you may need in order to put in a piecewise function. Okay, so let me do another picture so you can see y2 a little bit more. Okay, so now you can see y sub 2 a little bit better. Okay, so I'm sorry, like my whole screen kind of bounced around, but I wanted to make sure that you saw the rest of y sub 2. Also notice that y sub 2 and y sub 3 are now highlighted. The equal sign is bolded. You can do that with pressing enter. And I also took off y sub 1. So if you want to hit graph, okay, you're going to be able to see what its graph looks like, but we can actually do this by hands. Okay, I moved the screen over, so I'm going to have to put this a little bit further down than I wanted to. Okay. So we have f of x here, here's y, and let me label. There's negative 1, 1, 2, 3, 4, Okay, so you should be doing the same thing in your notebooks. So since the first piece is exactly the same as what we had before, we kind of know what's happening, you know, with its graph. Looks like a line with a hole in it. Okay, let me make that hole a different color perhaps. Okay, I don't think that's coming out clearer, but I'm indicating it the best I can. So now the next part is that for g of x, when x is 1, y is 1. So there's a point down here. I'm trying to make that green. So this is g of x. Okay, this is what's going on with g of x. So they're completely different functions. Okay, so now we're going to go to our next function, h. Okay, I'm not going to show you, the table or anything for h, but maybe I should have shown you the table for the piecewise function. It would say error like it did for y sub 1, for y sub 2, but for y sub 3, it would only have a value for when x was 1. So let me see if I can pull that up. In the meantime, I'm going to draw h of x. Okay, so here we go. There's my line, more or less. And with this line, that is off, but for every x, y is defined. There's no holes, there's no breaks, there's no gaps or anything. So here we go. Here's our 3 functions. Okay, and here is what g of x looked like. I didn't show h of x. I feel like it's a straight line. We all know how to graph that. So now let's get to finding the limit, and I'm going to show you 2 different tables. Okay, so you can see I'm asking A, the limit of f of x as x approaches 1. B, I'm asking what is the limit of g of x as x approaches 1. And C, the limit of h of x as x approaches 1. So write those down as I start to describe the different tables. Okay, so these tables are showing that the x values are getting very, very close to 1. We say from the left and from the right. From the left means there are less values than C, right? So 0.99, 0.999, 0.99999 is less than 1. Okay, on the right side, okay, are values that are greater than C. So 0.01, 1.001, 1.0001. Sometimes the tables are a little reversed, like in your... So in the textbook, as I was saying, I kind of lost track here, is that this may be like a different order. Just remember when you're trying to look at the table, you look as it gets closer to 1, okay? Either as values increase towards 1 or decrease towards 1. So this table is actually something we can do in our graphing calculator if we change independent over to ask. So I'm going to take a picture of that. Okay, when you go to table setup, it doesn't matter where your table starts or what the increments are, that's delta table. The only thing you need to change is where it says independent, you're going to go from auto to ask. Okay, the second table that I have here is where you would use auto because you can see that the increment is the same. Okay, it seems that we're going up by an increment of 0.001. So that's where we would put delta as 0.001. So I'm going to show you what the table set would look like for that. Okay, and as I'm describing this and these pictures are coming up, you should be writing down the 3 problems that we're doing, and perhaps a table you already decided you wanted to use. You don't have to actually write out both tables unless you want to be thorough. So here's the table setup, and I make it start at C, okay, whatever C is, in this case is 1, I make my table start at, and you're going to see why. Okay, so here's the CY. I just move where it says 1 down, so I can then adjust and see like 3 values before it and 3 values after. You should always have at least 3, if not more, values before and 3 values after. So I adjusted this for part A. I actually had done this before for part C, but they actually turn out to be the same tables. If you notice that when X is C, this is left as a question mark because we're not concerned with the function values, okay? Remember number 2 that you wrote down, the limit of a function as X approaches C may be defined as X equals C, it may not be defined as X equals C. So it doesn't matter what in the world this is, that is of no concern. We just need to know what's coming before and after. So for F, G, and H, this is a great example because the tables are exactly the same. Okay, like Y sub 1. Okay, I'm going to do this one first because it's what's left in my calculator. I scroll over to Y sub 1, make sure you see all of the decimals, but I only had 3 here. It's 1.997, then it slowly increases and increases. It makes sense, since it's slowly increasing, that the next answer would be 2. Okay? So you're thinking that could be the limit. Maybe it is, maybe it isn't. You have to check with the other side. Okay? So on the other side, this is slowly decreasing, and if you look at its values, okay, it's decreasing by 0.001. It makes sense that your next answer would be 2.000, maybe 1. So that side, it makes sense that the answer is 2. So both answers are 2. That is its limit. Okay. I just want to say that even the textbook does this. This question mark here is not the question mark there. Okay. Now, if you do G and H, you're going to end up with the same kind of answers depending on which table you do. So let me put in the other table here. Okay, so from the left-hand side, it seems to be 2. From the right-hand side, it seems to be 2. Both answers are the same. That is the intended height. If you had different answers, that's not the intention, okay, coming from both sides. Okay, it has to be one particular numeric answer. So in all of these cases, okay, the limit is 2. All right, that is the intended height. Like if we needed to fill in that hole, it would be when y is 2. Even though x is 1 here, okay, the intended height was supposed to be 2. Perhaps someone messed up and they put the point in a different place, became a different function, we had g of x. H of x is pretty straightforward. That's where it actually is defined. Okay? So this is where a limit exists. Okay? And you can see all the different scenarios that where it may not be defined, it may be defined. So just be careful. All right? And try to find the limits by predicting it from the table, see what's going on from the left and the right. Also notice I did not say, hey, just find these two and average them. Do not do that. Okay, I know my voice probably sounded really scary there, but do not do that. It is purposely changed so to emphasize that is not how you find a limit. All right, I'm going to give you some practice to do. I apologize for the lengthy video. They're usually not this long, but I had so much to show you on the graphing calculator and such. So good luck.